Welcome back, everybody. In this video, we're going to take a look at a LED blink program with the PIC 18F4550 with an internal clock, and then also redo the same program with an external clock. And also, we're going to take a look at the microchip C18 compiler delays.h functions for delays in our programs. So you might be wondering, I can already make a LED blink. Why should I have an internal and external clock LED blinking program on my computer? Well, there's multiple good reasons. One reason is that you're essentially going to end up with two different settings of chip configurations, one for an internal clock and another one for an external clock. So the next time you're starting a program, rather than doing all the chip configurations from scratch, you can simply open up either the internal or external clock example that you have and then copy and paste those chip config settings into the program that you're doing at that time. So that way you won't have to enter your chip config settings from scratch each time. Also, these programs are very useful when debugging. So what do we mean by that? What we mean is, inevitably when you're doing a big project, you'll have all kinds of fancy wires on your breadboard, doing every different thing, every which way, and then you'll go to turn it on, and the first time it won't do anything. So what do you do then? Well, the best first thing to do to make sure the chip is at least getting the power that it needs, the ground that it needs, that it's able to read the oscillator and do basic functions, is you can load one of the blink programs into your chip. Of course, you'll have to put a LED on your board if you don't already have one, but load that in there. Just make sure you can get a LED blinking, because maybe there's something fundamental that the chip isn't even getting, and then once you know you have that, you can debug from there. Also, if you're ever using the external clock in a program, so you have your big project all set up, you turn it on, nothing happens. If you load the external clock blink and still nothing happens, and then you load the internal clock blink and then it blinks the LED, then you know that somewhere from the oscillator to the chip, the oscillator is getting lost. So that's a good way to isolate the clock versus the rest of your project. Also, you might be wondering, why should I use the delays.h functions in the program rather than making my own delay functions? Well, really, the delays.h functions are recommended by microchip C18, and they're included in the compiler because they're much more precise. And also, if you ever change to using the optimizing compiler and you write your own delay functions, and again, the optimizing compiler is the pay version of the C18 compiler, then the optimizing compiler might optimize out your delay routines. So it's really better to stick to the recommended delays.h functions. So let's get started. So here's the circuit that we're going to use for our internal clock blink program. This is in fact the same circuit as in the very first tutorial for the 18F4550 for the blink demo board. And there's nothing especially fancy or elaborate here. We have a programming header up here, and then 4 LEDs, resistors to match, and then power and ground, and 1 smoothing cap for power. So here's our 18F4550 blink internal clock.c program and all of our chip configuration settings. So recall from the first tutorial series, if you're interested in the details on what these settings are, you can go to Help, Topics, PIC 18 Config Settings, and then you'll choose your chip. So for us, that'll be 18F4XXX, and then PIC 18F4550, and there we are. So most of these settings, we're simply going to turn them off. For example, the watchdog timer, the brownout reset, we don't really need all that. In fact, that might cause our chip to reset when we would rather that it didn't. So we'll turn most of these features off. There are some features here that you should be aware of though. And one of them is this USB voltage regulator enable bit. If you're using USB communication, you definitely want to set that to on. And also the first 4 settings are especially critical. PLL prescaler, system clock, USB clock selection bit, and oscillator selection bits. Of course, this is the one where you choose the internal or the external clock. So here we're using the internal clock, so we're going to set FOSC to INT OSC IO, so that's internal oscillator, and then we'll use the clock pins potentially for IO if we need to. So then scrolling down here, we're going to add delays.h so that we can use the delay functions in our program. So the rest of this is pretty much the same as the first tutorial, only we've taken out the delay function that we wrote in that tutorial, and now we're going to add here and here, we're going to add the delay functions from delays.h. Okay, so the next thing we're going to do is we're going to take a look at the delays.h header file to see the functions that are there. So if at least if you stuck with the default directory location for the C18 compiler installed, that's going to be C. If you're on a 64-bit computer, program files x86, microchip, and then MPLAB C18, and the latest version is 3.42, and then H, and then delays.h. And here's delays.h. So let's take a look at some of these functions. So for example, TCY is short for time of instruction cycle. You're going to see that abbreviation in all the delays functions. So for example, if you call delay 1 TCY, that's going to delay 1 instruction cycle. If you call delay 10 TCYX, that's going to delay 10 times the time for 1 instruction cycle times the parameter that you pass in here, which is what the X is referring to. Now notice that these parameters are unsigned characters, so you can't pass in a number larger than 255. So for example, if you need a delay of 1,000 times as long as TCY, you can't pass in 1,000 to one of these functions. That won't work. What you have to do in that case is pick a longer function. So for example, if you were looking for a delay of 1,000 times TCY, you would call this function here delay 1 K. K means 1,000 here. TCYX, and then you'd pass in 1, and that would give you your 1,000 factor delay. Okay, so next let's take a look at the calculation that we're going to do to make our LED blink visible. So TCY, of course, is short for time of instruction cycle, and since we did not adjust the OSCON register and we're using the internal clock, that's going to give us a 1 megahertz CPU clock. And also the 18F4550 uses 4 cycles per 1 instruction. Now let's say that we're going to have our desired delay for the LED blinks be a half second. So in other words, the LEDs stay on for a half second, then the delay time ends, and then they go off for a half second, delay time ends, and so on. So 1 time a second the LED will cycle. So here's how we can determine what we need, which function we need to call, and what parameter we need to pass in to get that half second delay. So our chip has 1,000,000 clock oscillator cycles per 1 second, and 1 instruction corresponds to 4 cycles. So if we multiply here, cycles cancel out, and then we have 250,000 instructions per 1 second. So if we invert that, then we have 1 second per 250,000 instructions, or 4 times 10 to the negative 6 seconds per instruction, which again is the definition of TCY. So TCY equals 4 microseconds. So what we're next going to do then is take the desired delay divided by TCY. So our desired delay is a half second divided by 4 times 10 to the negative 6 seconds. So in other words, we need 125,000 times TCY. So if we go to delays.h, what we'll find is this function here, delay 1k TCYX. And we can simply call that as follows. We can call delay 1 K TCYX and pass in 125. Remember, this can go up to 255. So here's how, if we want to check our math on that, here's how we can break it out. So delay 1, sometimes that'll be 10, but in this case it's 1. So 1 times the K is short for 1,000 times TCY, which again from up here is 4 times 10 to the negative 6th times 125, because that's a factor that we're passing in, and that's going to multiply out to be our ideal 0.5 second delay. So now we can simply enter that into our program twice. As follows. Delay 1K TCYX 125. And let's comment that. So if we go back to look at this and say 6 months, we're not going to wonder where in the world did we get that 125 from, but rather we'll have it nicely documented so we can follow what we did. So TCY equals 4 microseconds. So the delay that this function is going to cause is going to be 1 times 1,000 times 4 times 10. I'll use the caret symbol for exponent. 10 to the negative 6th times 125 is going to equal our desired delay of 0.5. And then we can simply copy and paste the same function to delay for a half second after the LEDs are turned off also, and then save it and compile it. And build succeeded. Now we can load this program into our chip. Alrighty, so now our board's all ready. So we're going to import our program, blink internal clock.hex, and go ahead and write it. And there we go. Programming successful. And we'll turn the power on. And there's our nice 1 second per cycle LED on-off delay. Alrighty, so now we're ready to throw the clock on our board. So here's the diagram for our external clock circuit. The LEDs and resistors, programming header, power ground, smoothing cap, that's all the same. The only difference is we now have a 20 megahertz oscillator on pins 13 and 14, and those go to 22 picofarad caps, which go to ground. Okay, so now that we have our external 20 megahertz oscillator crystal on our board, we can take a look at our updated chip config settings. So again, after these first four here, the rest are pretty much the same. The one setting that we do want to note is the VReg enabled setting to on. That's voltage regulator enabled, which is the USB voltage regulator. So what we're going to do is if we set this to on, and then we put a capacitor on pin 18 of our chip, then that will allow us to do USB communication using the internal 18F4550 voltage regulator for the USB circuitry. If you really so choose, you could turn this off and then feed an external voltage regulator to the USB circuitry, but that's really not necessary. It's much easier to simply leave this on and then put a capacitor on pin 18 when you're doing USB communication. So also, let's take a look at these first four settings. So if you're interested in the details in these settings, and I won't go into all the details here, but what you want to do is you want to check the 18F4550 datasheet figure 2-1 clock diagram. So what we're going to do is we're going to set FOSC to high speed, phase lock loop high speed. And what that's going to do is that's going to use 48 megahertz for both the USB circuitry and also the general CPU circuitry of the chip. And we're going to set PLL div to 5, CPU div to OSC1, PLL2, and USB div to 2. So let's take a quick look at this figure 2-1. So here's the 18F4550 datasheet figure 2-1 clock diagram. And here's what we're doing. We're feeding our 20 megahertz oscillator into OSC1 and OSC2 here on the left. Those are our pins 13 and 14 on our chip. And then that signal goes into these gates here, the PLL prescaler, and then into the phase lock loop, which actually gets the frequency up to 96 megahertz momentarily before dividing it by 2 and then taking it back out here where it's labeled USB peripheral. That actually means the clock for the USB circuitry. And also, the way we have it configured, the same 48 megahertz signal coming out of the phase lock loop goes down here into the PLL post scaler and then through the CPU div gate here, and then becomes the CPU clock also. So in our case, both the USB peripheral clock and the CPU clock are going to be 48 megahertz. Okay, so now we're ready to get back to our program. So other than the chip config settings, this program is going to be the same as the last one, except for the amount of delay time, of course, but we'll get to that in a moment. First, let's remember to include delays.h. Now we have to decide what are we going to put for our delay time. Well, here's how the calculation is going to work out with the 48 megahertz clock. So as before, time TCY is still short for time of instruction cycle, but now we're working with the 48 megahertz CPU clock. And still, as before, there's 4 cycles per 1 instruction. So if we do 48 million cycles divided by 1 second times 1 instruction per 4 cycles, cycles cross out, and we're left with 12 million instructions per 1 second. So if we invert that, 1 second divided by 12 million instructions equals 8.333 times 10 to the negative 8th seconds per instruction. In other words, 0.08333 microseconds per instruction, which is our TCY number. So as before, we're going to do desired delay divided by TCY. So we'd like to keep the delay still at a half second. So 0.5 seconds divided by 0.08333 times 10 to the negative 6th. It's going to equal 6,240,000. Now this is something that's blinking and turning off for human perception. So out of 6,240,000 really isn't significant. So we can simply round that off to being 6,240,000. times TCY is the delay we're looking for. So if we go to delays.h, we see the longest possible delay we can call here is delay 10k TCYX. And remember, you can't, since these parameters are unsigned characters, you can't pass in higher than 255 here. So let's see if what happens if we pass in 255. Well, then we're going to call delay 10k TCY times 255. So 10 times 1,000 times 0.08333 times 10 to the negative 6 TCY time times 255 still only equals 0.2125 seconds. That's not long enough. Remember, we're looking for a half second. So what are we going to do? Well, let's do it this way. Let's call delay 10 KTCY and then pass in 120. So that's going to give us a delay of 10 times 1,000 times 0.08333 times 10 to the negative 6 times 120, which works out to be 0.1 second, and then we'll simply put a for loop in that's going to call this function here 5 times, totaling a delay of 0.5 seconds. So here's how all that's going to work out for us. So we have to make sure to declare our loop variable I at the top, and then we're going to type for I is assigned 0 while I is less than 5, I plus plus, delay 10 KTCYX, pass in our 120, and then we'll comment that. So TCY, time of instruction cycle, equals 0.08333 microseconds. So the total delay that this line is going to cause is going to be delay equals 10 times 1,000 times 0.08333 times 10, again I'm going to use the caret symbol for exponent, 10 to the negative 6th, times 120 that we're passing in, times the 5 times in the for loop that we call the function. So that's going to work out to be a delay of 0.5 seconds. And now we can simply copy and paste that for our second delay. And now we can go ahead and compile our program and then load it into our chip. Okay, so now we're ready to load our program into our chip. So let's go File, Import Hex, 18F4550 blink external clock.hex. Successfully imported. Write. And as soon as that's done writing, zoom in and turn the power on. And there's our nice 1 second cycle time for our LEDs, just as before. So now we've achieved the same 1 second cycle time with the 1 megahertz clock and the 48 megahertz clock. Congratulations! You now know how to set chip configuration settings for both internal clock and external clock use with the PIC 18F4550, and also how to calculate delay times and call delays.h functions for precise delays. In upcoming videos, we're going to take a look at 18F4550 timer and interrupts in an example, and also a motor controller example, and then after that, a USB motor control example. See everybody next time.